Hello and welcome back to this Astronomy 101 series. So last week I sort of left you on a cliffhanger. I told you all these patterns and things about the solar system that we'll have to explain, but then I didn't actually explain anything. So that's what we're going to do tonight. I'm going to explain all of the things we talked about yesterday, the reasons why we have these large-scale patterns in the solar system. And that has to do with the formation of the solar system. But before we get too much into that, here is tonight's quote from Georges Lemaitre, a French Catholic scientist. He said, "The evolution of the world may be compared to a display of fireworks that has just ended. Some few red wisps, ashes, and smoke. Standing on a cooled cinder, we see the slow fading of the suns, and we try to recall the vanished brilliance of the origin of the worlds." Very beautiful quote there. All right, so last week we talked about these four different characteristics of the solar system that we're going to have to explain. Here's a little quick review. So there's tons of patterns of motion among the planets. So all of the planetary orbits are nearly circular. They all lie in the same plane. All the planets orbit the sun in the same direction, counterclockwise, if you look down at the solar system from above the Earth's North Pole. Most of the planets also rotate in that same direction with small axial tilts. The sun also rotates in that direction as well. And then most of the large moons of the solar system, those big spherical ones, exhibit similar properties to the solar system, just in their orbits around their planets. We also have two populations of planets: terrestrials, Mercury, Venus, Earth, and Mars, and the Jovian planets, the gas giants, Jupiter, Saturn, Uranus, and Neptune. There's also a lot of asteroids and comets. The asteroids sit in the asteroid belt between Mars and Jupiter. The comets tend to stay out in the outer solar system beyond Neptune and the Kuiper belt, or the spherical distribution called the Oort cloud. And then there are also some weird exceptions that we have to explain, like the axial tilts of Venus and Uranus. Venus is completely flipped upside down. Uranus rotates on its side. And we also got to explain stuff like the size of the Earth's moon, which is uncharacteristically large given the size of its planet. So all of this stuff we've got to explain, and it can all be traced back to how the solar system was formed. And we can generally trace the origins of our theory about how the solar system was formed to these two guys. So we have the German philosopher Immanuel Kant on the left, and the French polymath Pierre-Simon Laplace on the right. Kant came up with the idea first in 1755. He proposed that the solar system formed from a gravitational collapse of an interstellar gas cloud. That's pretty spot on, actually. About 40 years later, Laplace independently came up with sort of the same idea. His was a little more complicated, as mathematicians are wont to make things. He said that the sun originally had an atmosphere that extended throughout the entire solar system, all the way to the orbits of Neptune. And as the sun cooled, it contracted and it collapsed, and parts of that sun were thrown off into gaseous rings, and the planets formed out of those rings. Now, that was a great idea for the 19th century. But slowly, as we learn more about the solar system, there were things that couldn't be explained by Laplace's idea. And so a bunch of people came up with other ideas. Here's just a selection of them. So we have the Plantastical theory by Thomas Chamberlain and Forrest Moulton. I think Chamberlain was actually a geologist. Tidal theory by James Jeans, who's done a lot of other work in astronomy, and accretion theory by Otto Schmidt. Essentially, all of their different theories revolve around what is essentially called a close encounter hypothesis, that in the early history of the solar system, a different star from our sun, passed very close to our sun, and the gravitational interaction between the two stars caused globs of material to come out of our sun. And those globs eventually cooled and became the planets as we see them today. Now, by the mid to late 20th century, this hypothesis was not a good one. This theory couldn't explain some of the things we see. So the theory would not reproduce the dichotomy of the planets that we see. We have the terrestrial and the Jovians. Excuse me. This theory wouldn't hold up to just how far apart stars are in our galaxy. For another star to come that close to the sun would be such an improbable event as to make it an untenable scientific theory. So uh, by the mid to late 20th century, these ideas were kind of on their way out. As fast as they came in, they were on their way out. But thankfully, we made some new discoveries about the physics of planet formation, and we modified Laplace's nebular hypothesis a bit. And by modifying that hypothesis, it became a little more in line with how the universe actually works. And it works so well that we elevated the nebular hypothesis to the status of a theory. So now it's called the Nebular Theory. And that's what we're going to talk about tonight. We're going to talk about the Nebular Theory and how it explains the formation of the solar system. All right, so the Nebular Theory begins with the idea that our solar system was born from the gravitational collapse of an interstellar cloud of gas, which we will just simply call the solar nebula. And it collapsed under its own gravity. This cloud gave birth to the sun and the planets in a spinning disk that formed around the sun. You may be asking the question, where did the gas that formed that interstellar cloud come from? Well, you can trace it all the way back through billions of years of galactic recycling from previous generations of stars. So recall that the universe was essentially born from the Big Bang, which produced only two elements and a smattering of some other things, but only two major elements, hydrogen and helium, and a smattering of lithium and maybe some beryllium. The heavier elements were produced later by stars doing nuclear fusion in their cores. You only get stuff heavier than helium by doing nuclear fusion. Those heavy elements, once those stars died in supernova explosions, once those heavy elements were then mixed into the gas that's a part of the galaxy. And that new recycled gas would go and then form new stars. And that's the whole process. So each new generation of stars is giving more and more metals, more and more heavy elements to the gas of the galaxy. Despite all this recycling that's happening, it hasn't added much metals, much everything else to the galaxy. So the gas cloud that made up what later became the solar system consisted by mass of about 98% hydrogen and helium and 2% everything else. And there's a lot of strong observational evidence that supports this scenario. So spectroscopy of old stars have a smaller proportion of heavy elements than the younger ones, just as we would expect if they were born at a time before many heavy elements were manufactured. Moreover, visible and infrared telescopes allow us to study stars in the process of solar system formation today. So this is a beautiful collection of images from the Hubble Space Telescope of the Orion Nebula. You see the beautiful Orion Nebula in the background, but then little insets are solar systems being formed. You see disks of gas, of heated gas around each of these stars. And so just as our scenario predicts, these stars are surrounded by these disks of gas, and they have the characteristics that match what we would expect if they were collapsing due to gravity, if these were actually solar systems being born. So there's tons of evidence to support this whole nebular theory idea. But now let's try and explain some of the major things in the solar system. So initially, the solar system probably began as a large and roughly spherical cloud of very cold, low-density gas. Now, this gas was so spread out, this gas cloud was so large that gravity probably actually couldn't pull it together. It was probably just kind of floating. There might have been some random motion, maybe it was slightly spinning, but for the most part, it would have just kind of hung out. What caused it to collapse, we think, was a triggering event. Something had happened nearby, maybe a shock wave from a nearby supernova, maybe a change in magnetic fields, if the gas cloud was electrically charged. Well, it could be a whole host of things. We'll go with the supernova theory for now. But something pushed the gas cloud and allowed it to become unstable and collapse. And once that collapse started, gravity will make that process accelerate, increasing with strength. But there are also some other physical laws that are in play to explain the general patterns of motion that we see today. So, as the solar nebula shrank in size, three important processes altered its density, temperature, and shape. So, the first is heating. The temperature of the solar nebula increased as it collapsed. This heating actually represents what we talked about a few weeks ago. This is the conservation of energy here. As the cloud shrank, the gravitational potential energy in the cloud was converted to kinetic energy of the individual particles. And then those particles crashed into one another, converting the kinetic energy of their inward fall to the random motions of thermal energy. And then the sun formed at the center where the temperatures and the densities were highest. The next thing is spinning. So just like an ice skater pulling in their arms as they spin, the solar nebula would rotate faster and faster as it shrank in radius. This is the conservation of angular momentum. The rotation of the overall gas cloud before it collapsed might have been imperceptibly slow, but as it collapsed, conservation of angular momentum, as the radius shrinks, the velocity has to grow. But that also meant that not all of the material fell into the center, because it has to be, as it's collapsing, it's going to spread out into this sort of disk. The greater the angular momentum, the more spread out the disk will be. And the final process is flattening. So the solar nebula flattened into a disk. And this is a natural consequence of the conservation of plain old momentum, not angular, but just linear momentum. A cloud may start with any size or shape, and different clumps of gas within the cloud may be moving in random directions at random speeds. But those clumps will collide and merge as the cloud collapses. And each new clump has the average velocity of the clumps that formed it. And so the random motions of the original cloud therefore become more orderly as the cloud collapses, changing the cloud's original lumpy shape into a rotating flattened disk. Similarly, collisions between clumps of material in highly elliptical orbits reduce their eccentricities, making the orbits more circular. Essentially, flattening makes everything orbit in a circular orbit and in a nice single plane. And so the formation of this spinning disk explains all of the patterns of motion that we see in the solar system today. The planets all orbit the sun in nearly the same plane because they all formed in a flat disk. The direction in which the disk was spinning became the direction of the sun's rotation and the orbit of the planets. The fact that the collisions make orbits more circular on average explains why the planets have nearly circular orbits. Computer simulations have shown that the planets would also tend to rotate in the same direction that they formed. We can test this model by looking out into the universe and trying to find solar systems in the process of being born. So primarily in the infrared, if we look at young stars, we see the telltale signatures of solar system formation. So the bottom left are images from the Hubble Space Telescope of two stars on the top are the actual images, and then the two on the bottom are computer-generated graphics representing what those images are representing what those images are showing us. On the right is a collection of actual images from the Atacama Large Millimeter Submillimeter Array in Chile. Very young stars with hot dust, hot gas surrounding them. These gaps in the bands might be where some planets are being formed. They've swept up the material in the gaps. This is all, proof that this whole nebular theory is doing what we want. You see, they're all flat disks. They're all rotating. This nebular theory happens to be correct. We also use computer simulations to test the model. So this is a beautiful simulation of perturbations in the rotating disk going on to form a few planets here. You see the knots, the bright yellow orange knots, those are where planets are being formed. Some of them might collide, some of them might fall back into the star, but some of the planets will survive and to the present day. So it was a very cool simulation. All right. So that's how the major patterns of motion can be explained by the nebular theory. What about the two types of planets here? So the planets began to form after the solar nebula had flattened into the disk of maybe about 200 astronomical units in diameter, about twice the present day diameter of Pluto's orbit. The churning and the mixing in the gas should have ensured that the nebula had the same composition throughout. The materials were spread evenly throughout the disk. So then how did we get terrestrial planets on the inside and gas giants on the outside? And so the key comes from their locations in the solar system. The terrestrial planets formed in the warm inner regions of the swirling disk, and the Jovian planets formed in the colder outer regions. So in the center of the solar nebula, the gravity drew together enough material to form the sun. But further out, the gaseous material was too spread out. It was too sparse for gravity to clump it together. Instead, the material had to clump together in some other way and then grow in size until gravity could start pulling more things together. In essence, the formation of the planets required first the formation of seeds, basically just little solid bits of matter that could ultimately build planets. This is similar to how snowflakes form in the clouds here on Earth. They don't just, they have to condense out of the water vapor. Similarly, the planets have to form out of the gas at low enough temperatures. Some atoms or molecules in the gas may bond and solidify in a process known as condensation. And those particles will start out microscopic in size, but they can grow larger with time. Now, the key part here to explain why we have two different types of planets is the fact that different materials condense at different temperatures. So here you see a plot of the planet's modern day distances from the sun on the horizontal axis, and on the vertical axis, the temperature of the solar nebula when those planets were forming. So remember, the solar nebula is made mainly out of hydrogen and helium. 98% of the solar nebula doesn't condense at any temperature. It will always just be some sort of gas. You won't get a solid out of hydrogen and helium at any of the temperatures found in the solar nebula. However, hydrogen compounds, remember those are ammonia, water, methane, stuff like that. Those will condense into ices below about 150 Kelvin. So I've drawn this blue line here on this plot. And look, all of the gas giants are below that line. Interesting. Rock makes up much less of the solar nebula, and it will condense into solid form between 500 and 1300 Kelvin in this brown box. So everyone but Mercury and maybe Mars are in it, so Venus and Earth. Metals will condense at temperatures below 1000 to 1600 Kelvin, so anything below here. So Mercury, definitely made out of metal. So these materials would condense whenever the temperature allowed. Close to the sun, it was way too hot for any material to condense. But a little farther out near Mercury's current orbit, it was cool enough for metals and some types of rock to condense out of the solar nebula into tiny little particles. But all the other types of rock and the hydrogen compounds remain gaseous. Further out at the orbits of Venus and Earth, then more types of rock could condense. In the region where the asteroid belt would eventually be located, temperatures were low enough to allow dark carbon-rich minerals to condense, along with minerals containing a small amount of water. And then it was cold enough for hydrogen compounds to condense into ices beyond the frost line. which was between the current orbits of Mars and Jupiter. All solar systems have a frost line, basically where water will be either a gas or a solid. So the Jovian planets, the gas giants, all beyond the frost line. So they'll have ice to aid in their formation. Meanwhile, inside, we're just have to rely on the metals and the rocks. So to build the terrestrial planets, they've got to only rely on the metals and rocks. But because there's not much metal or rock in the solar nebula as a whole, the terrestrial planets are going to be very limited to how big they can grow, just because there's not enough material to form them to make them really, really big. The process by which the small seeds grew into the planets is called accretion. So accretion began with the small particles, and these small particles had pretty much the same orderly circular paths as the gas. So collisions between these small particles were more like gentle touches and actually collide and stick. What caused them to stick was not gravity, but if these particles were slightly electrically charged, then electrostatic force, static electricity, essentially, the same thing that makes your hair stick up when you combed it too much. Static electricity would cause the particles to stick together, eventually growing large enough for gravity to take over and then accelerate that growth, making these small seeds become planetesimals. Not planets yet, but something smaller, planetesimals. This planetesimal growth happened very rapidly in the first few million years. But once they reached about 100 kilometers in size, the growth became a little bit more difficult. And that's because gravity would alter the planetesimal orbits, which would make them cross each other, and their large sizes made those collisions more destructive than constructive. So eventually, only the large ones survived to become planets. Here's two different simulations of terrestrial planet formation in our solar system. So I'll start at the top left one first. I put bands here where the terrestrial planets are currently located in blue, and in orange where the asteroid belt is. If I press forward, you can see a bunch of planetesimals all sort of bobbing up and down. That's their eccentricities changing. How elliptical are their orbits? But they're also colliding and sticking together, either through electrostatic forces or eventually through gravity. And so you can see some of the planetesimals getting tossed out, really high eccentricities, some of them forming together to build bigger and bigger planets. So at the end of this simulation, we should have a few Venus and Earth, maybe a Mars that is a little bit too big, and very few things in the asteroid belt, at least in this simulation. That big black dot that hasn't moved is Jupiter. So this did a pretty good job of recreating what we see in the solar system. On the bottom right, we'll see the same thing, except instead of how eccentric their orbits are on the vertical axis, we will see their mass in Earth masses on the vertical axis. So we're starting out the simulation with a population of really tiny, low mass objects, and then ones slightly more massive, and we'll see how they work together over the millions of years. They're colliding and they're bumping each other up, combining to form objects. Roughly what we get from the planets today. That's pretty accurate. There you go, with that simulation. When it comes to the Jovian planets, accretion will still happen out here. It should happen pretty much in a similar way to the inner solar system. But out here, there's way more material to use since we're beyond the frost line out in the gas giants. And so ice could condense out there. And so because there's so much more material, these planetesimals were able to grow much larger than in the inner solar system. And they grew so large that these cores, these icy cores, were able to use gravity to capture some of the hydrogen and the helium in the nebula, which then made their gravity stronger, so they pull in more gas et cetera, et cetera. This would repeat until we get the massive gas giants that we see today. But this also explains the large moons of the Jovian planets. That same process of heating and spinning and flattening that the solar nebula went through also happened to the gas that was drawn in to the gas giants. So you see here in this artist rendition that each of the gas giants had their own sort of mini solar nebula. And in those little mini solar nebulas, material would condense out of those and go on to form the big, large spherical moons of the outer solar system. So that's how we get the moons following the same patterns of the overall nebula, the overall solar system follows. Very cool. Now, obviously, the solar system is not filled with hydrogen and helium gas, and the outer gas giants are not large enough to have swallowed up all of the hydrogen and helium. So that makes us conclude that most of the hydrogen and helium in the solar nebula never actually went into forming the planets. So we must have gotten rid of it through some other method. And that was through high energy X-rays and UV light from the sun and the solar wind. So observations show that young stars tend to have much stronger solar winds and emit much more high energy radiation than older stars. So the young sun must have had a very strong combination of radiation and solar wind to clear the solar system of the gas, of the hydrogen and the helium. But doing that, clearing the gas, pushing all the gas back out into the galaxy, sort of sealed the compositional fates of the planet. So if the gas stayed around a bit longer, then over time it would have cooled. And maybe it would have cooled enough for that frost line to be moved a little bit further in towards the sun, allowing ices to be able to condense in the inner solar system, completely changing the nature of the terrestrial planets. Because the inner planets would be able to use ices and add that to their mass, and perhaps then they'd be able to pull in the gas that surrounds them. So we might not be living on a terrestrial planet if the gas stayed around longer. If the gas was cleared earlier, then there goes all the raw materials that we need in order to form the planets. The terrestrial planets might have been smaller. They might not be spherical. They might be too small to be spherical. The gas giants wouldn't be as giant. So at least for our solar system, it seems that it was cleared out at the right time for life to eventually evolve here on Earth. But this in turn allowed the sun to transfer some of its angular momentum to the gas. By blowing out this gas, it was able to get rid of some of its angular momentum, which is why the sun spins pretty dang slowly. About 2 kilometers per second is its rotation rate. It completes a solar day, a day on the sun is about the length of an Earth month. And that's pretty slow compared to other stars. So that explains why the sun appears to be spinning as slowly as it does today. So here's a beautiful simulation of the solar nebula flattening, and then the planets condensing out of that gas, and then the gas will eventually be blown away. So that is the sun, the early sun, blowing the gas out. The planets should have already formed by then, but this is an animation, so I'll give them a pass on that one. And there you go. You get the planets of the solar system. All right, so here's a question. Which lists the major steps of solar system formation in the correct order? So A, collapse, accretion, condensation, B, collapse, condensation, accretion, or C, accretion, condensation, collapse. So pause the video and come back to this when you've got your answer. All right, I assume you've got your answer. The correct answer is B. Remember, the whole thing has to collapse from the interstellar cloud. Then material has to condense out of the disk, And then finally those seeds will then be able to undergo accretion and grow to their present day sizes. All right, now we got to explain the origin of the asteroids and the comets. So the asteroids and comets are essentially the leftovers from the process of planet formation. These are essentially the planetesimals that didn't get to become planets, but only a very small fraction of all the planetesimals that were created in the solar system. Because most likely the rest were either thrown into space by gravitational encounters or collided with the planets, destroying themselves essentially. A vast majority of these impacts occurred during the period of heavy bombardment, which was during the first few million years of the solar system. Essentially, every world in the solar system was pelted by impacts during the heavy bombardment period. And most of the craters on the moon and the other terrestrial worlds date from this era. And now an important part, this was pretty hellish. Impacts constantly, lava, magma, whatever, all over the place. But remember, the Earth is inside the frost line, so water couldn't condense here. So how is Earth covered in water? Well, current theories put forward that comets from the outer solar system during this period of heavy bombardment, comets were able to form. They're made out of water ice, and they were able to essentially come into the inner solar system and collide with the Earth. And so it's likely that those impacts were the thing that brought water and other hydrogen compounds, possibly the ingredients for life itself, from the outer solar system into the inner solar system. So thanks to all these impacts, despite how hellish it might have been, it's thanks to all these impacts that we have water and eventually life here on this planet. All right, what about the exceptions? So we have captured moons. So moons that go in the wrong direction or of large inclination relative to their planet's equator are likely captured planetesimals. So remember, so just a refresher, inclination is how tilted your orbit is from a plane. So all of the solar system planets don't have very high inclinations, but the moons of the planet, some of them do. Some of them are tilted way above the plane of their planet's equator. These were likely captured objects, while the Jovian planets had a disk of gas surrounding them, which would give friction to these objects, causing them to lose their orbital energy and enter into these weird, highly inclined orbits. So here's the moons of Saturn. On the horizontal axis, we have distance in terms of Saturn radii, so 100 Saturn radii, 400 Saturn radii. On the vertical, we have inclination, how tilted are the orbits. Above zero, these are what are known as prograde moons. These are rotating in the rotating counterclockwise. They're in the correct way. Below zero are retrograde moons. They're rotating backwards, essentially. You know, once we define what backwards means, clockwise in our case. So here you can see the major and minor moons in green and yellow. They are all pretty low inclination. They most likely formed with Saturn. In fact, a few of them are in Saturn's ring, so they really did form with Saturn. Out here, we've got the Inuit and the Gallic moons, where they've got highly inclined orbits. Those are most likely captured. And then we've got the Norse moons with highly inclined orbits, but they're going in the opposite direction. Those are also likely captured objects. Remember, these captured objects come in from any direction. That's why we have two populations. Some are going the correct way around the planet. The others are going the incorrect way around the planet, because they can come from any direction and be captured. We also have to explain the creation of our moon. Capture processes can't actually explain how our moon came to be because it's too large and Earth is too small to capture such a large object. Look at the moons of Mars. Those are Phobos and Deimos. Those are two essentially asteroids. That's the size of moon Earth could capture. We could not capture the size of our moon. It also probably could not have formed simultaneously with the Earth, just like the Jovian planets had their own disks of gas forming moons around them. Earth could not have done that, because then both the moon and the Earth would be made of the same material at the same density. But the moon's density is about 60% of the Earth. So it means it's made out of different material. So it can't have been like that. The leading hypothesis is the giant impact theory. So a Mars-sized object named Theia hit Earth, but at an angle. It kind of skimmed Earth, and that caused the Earth's outer layers to be blasted into space, which then collected in an orbit around the Earth and formed the moon over the course of maybe a few weeks to a few months. Here's a beautiful simulation of that impact. You see immediately a ring. Theia sort of survives the impact, but eventually comes back and collides with the Earth again, really destroying it this time. It's not going to survive that. But that material in the sort of half ring will condense into globs. Some of those globs will fall back on the Earth. Some of them will be shot out of the solar system. But much of the material will recombine gravitationally to form the moon, what we have today. And impacts can explain some of the other features that we see in the solar system. So going left to right, Mercury has a pretty dang large core. It should not have that big of a core. That gives it the second highest density of the planets in the solar system. Perhaps it was left behind after a giant impact that stripped Mercury of its outer layers, just like Theia did to the Earth, except in Mercury's case, it didn't get a cool moon out of that interaction. In the middle, Uranus famously is tilted on its side, perhaps another giant impact during its formation history caused it to flip on its side. And on the right is the end result of a simulation of an impact at Pluto that, at least according to this simulation, went and formed Pluto and its moon Charon and caused them to be tidally locked. Perhaps that's what happened out there. So impacts can sort of explain some of the other features we see in the solar system. Now you might be wondering, was this all simply a matter of planetary destiny? Was this always going to happen like this? Although nebular theory can tell us a lot about the formation of our solar system and explain a lot of the features we see, it doesn't mean that it was all destined to be this way. Other solar systems can be radically different from our own. So the same processes that formed our system of planets can lead to a completely different organization around a different star. This image, sort of a little raindrop image, are actual solar systems that we've discovered. Some of them have very big planets very close to their stars. Some of them have multi-planet systems. Some of them just have a single planet. What happened there? These are all things that we will talk about in several weeks when we get to exoplanetary systems. But truly, the way our solar system formed, it could have formed in a completely different way. Other things could have happened. It's not a matter of planetary destiny at all. All right, so given what you know about nebular theory, would the discovery of the following extrasolar system be reasonable or surprising? So a solar system has six terrestrial planets and 4 Jovian planets. Each of the 6 terrestrial planets has at least 5 moons, while the Jovian planets have no moons at all. Pause the video and think about your answer and come back and I'll tell you the correct answer. All right. Yeah, this would be very surprising. Not necessarily the number of terrestrial or Jovian planets, that would be fine. But the fact that in this system, the terrestrial planets all have 5 moons, while the Jovian ones have no moons at all, that's very surprising. Remember, the Jovians have enough gravity to essentially create their own little mini disk around them, forming moons out of that disk. Meanwhile, the terrestrial planets are too small to do that. And certainly, even after they've been formed, too small to hold on to 5 total moons each. That would be very, very weird. Something odd happened in that system. It would be very surprising if we found one like that. All right, so we've talked about how the solar system was born, but when was the solar system born? How do we know that? So we've essentially got to ask the question, how do we know the age of a rock? And we know the age of a rock through a technique called radiometric dating. So by measuring the proportions of various atoms and isotopes in a rock, we can calculate how long ago that rock was last solidified. So remember what an isotope is. An isotope is a chemical element that has a differing number of neutrons in its nucleus. So for example, carbon typically has 6 protons and 6 neutrons. So we call that carbon 12, 6 plus 6. But an isotope of carbon could have 6 protons and 7 neutrons. So we would call that carbon 13. So here are 2 isotopes, potassium 40 on top and argon 40 on the bottom. Potassium 40 is radioactive, so its nucleus will undergo some sort of spontaneous decay, such as either breaking into 2 pieces, such as happens in nuclear fission and atomic bombs, or by having a neutron turn into a proton. So in the case of potassium 40, I've highlighted a red proton. That red proton will spontaneously change into a green neutron. And so we go from, we lose the 19, but we add a neutron. That doesn't change the atomic mass number. So we go from potassium 40 to argon 40. Potassium is called the parent isotope. Argon will be the daughter isotope. Now, this all happens over a certain amount of time. So by studying a collection of a particular isotope, so we'll keep the same example of potassium 40. If we study a collection of potassium 40, we can watch it decay into argon 40 over a half-life. That's the time it would take for half of the parent nuclei to decay, half of the potassium 40 to decay. So to understand, every radioactive isotope has its own unique half-life, ranging from a fraction of a second to billions of years. The half-life for potassium 40 to argon 40 is 1.25 billion years. So to understand the idea of a half-life better, imagine a small piece of rock that contained 1 microgram of potassium 40 and no argon 40 when it solidified long ago. The half-life of 1.25 billion years means that half the original potassium 40 has decayed into argon 40 by the time the rock was 1.25 billion years old. So at that time, the rock contained a half of a microgram of potassium 40 and a half of a microgram of argon 40. Half of that half of a microgram of potassium 40 will then decay in the next 1.25 billion years. So after 2.5 billion years, the rock contained a fourth of a microgram of potassium 40 and 3/4 of a microgram of argon 40, and so on and so forth. You can see this graph kind of illustrates the idea. We've got on the horizontal the time since the rock formed in billions of years, and on the vertical we've got the fraction of isotopes. So if we start off with just potassium 40, no argon 40, over 1 half-life, so 1.25 billion years, we will lose half of the potassium 40 and gain an equal amount of argon 40. Over 2 half-lives, the original amount of potassium 40 has reduced to 1/4. 3 half-lives, half of a quarter is 0.125, and so on and so forth. That is how half-lives work. So suppose you find a rock with equal amounts of potassium 40 and argon 40. If the argon 40 came from this decay chain, then the rock must be 1.25 billion years old. This is where it's useful to know a little bit about rock chemistry. Potassium 40 is a natural ingredient in many rocks, but argon 40 is a gas that does not combine with other elements, and so it could not condense in the solar nebula. So if you find argon 40 gas trapped inside minerals, it must have come from the radioactive decay of potassium 40. So this is how we use half-lives to deduce the ages of rocks and minerals, and how we will use it to radiometrically date the Earth. So we find many rocks of different ages on the Earth. So obviously the youngest ones were just formed from molten lava. You can go to Hawaii or any place where there are active volcanoes to find very young rocks that were formed, a second ago. While the oldest, and particularly there's a region of Canada as some of the oldest rocks in the world, are about 4 billion years old. So an example of that is this nice rock that's about 4.03 billion years old. But the Earth's surface has changed over time. It's not only wind and water have eroded things, but the continents move. Plate tectonics, which we'll talk about next week, have caused some rocks to be subducted into the Earth's core. So the oldest rocks aren't as old as the Earth. We could go look at the moon. The Apollo astronauts brought back moon rocks that have been dated to be about 4.4 billion years old by looking at the half-life of uranium-238 contained in those rocks. So one such rock has been nicknamed Big Bertha, was brought back by the Apollo 17 astronauts. But that's still not the age of the solar system, since the impact that formed the moon happened after the solar system was mostly put together. So we've got to go look for rocks that are completely untouched. We've got to find rocks that have not melted or vaporized since they first condensed out of the solar nebula. And those are meteors. So the meteorites that have fallen to Earth are the most pristine rocks to be radiometrically dated. The oldest ones were formed about 4.56 billion years ago. So that must mark the beginning of accretion in the solar nebula. And so because the planets apparently accreted within about 50 million years after that, according to our simulations and our other research, Earth and the other planets have formed by about 4.5 billion years ago. In other words, the age of our solar system is just 1/3 the 14 billion year age of the universe. So I'll leave you with that fun thought tonight. So that's that. That's the formation of the solar system. Next week, we will start with the geology of the inner planets. We'll talk about their surface and their interiors as well. So definitely look for that. With that, I will say good night. Thank you for watching. Make sure you comment down below if you've enjoyed these so far, and I will continue to do them. All right, have a good night.